Okay, so we're going to be starting chapter 3, which is exponential functions. Okay, that's bittersweet because within exponential functions, we have to talk about logarithms. And that is not people's favorite topic. But if you had me, if you were with me last year, we beat that to death. Okay, you got plenty of logs. You should be comfortable. If not, then you got a second chance this year to nail that down and make sure it's a piece of cake. So, logs are later. Let's talk about what should I know from exponentials. So let's go back just a little bit and talk about what's the old news that I need to know. So look on the screen. You've got all this exponential rules. Okay? And so here you have some basics. I am not going to be teaching that. All this stuff over here, this is old news. If you don't know these rules, then when we do some of our problems, you're going to be kind of lost and talking, well, how did you get that to work out? Well, why did this do this? Those are the questions that students that don't know their background, they're going to ask those questions. Did you catch that, some of you? If you don't know this, you're going to be asking embarrassing questions that you shouldn't be asking. Know these. This is going to be foundational. Now, it won't come into play too much at the beginning, because at the beginning we're going to be looking more on the graphing side of things, and then we'll get into solving equations, combining things, and simplifying all this other stuff. Today we're going to kind of just introduce it. So let's talk about what do we do if I had to apply some of these. Just some basics. So try this. If I give you a function, and that function is 2 to the x, I'm going to give you 5 different functions that I want you to try. So you have a through e. Plug those in and simplify as far as you can by hand. But not, if you got to go to a decimal and you finish it, leave it alone. So just take a minute or two and see if you can simplify that. All right, so first part, f of 4 is equal to what? It's equal to 16. Okay, what about f of 0? And what do we know about that? Anything to the 0 power, anytime you got this scenario happening, anything, variable, a number, an expression, anything to the 0 is always going to give you a result of 1. That's a nice thing to happen. That clears up a lot of stuff. Okay, what about negative exponents? What do we do with negative exponents? I think we got that right there. Negative exponents mean do that. Flip it. What if the exponent's already in the fraction, and it's on the bottom, and it's already negative? What happens to it? You still flip it up to the top. Okay, it just makes it a reciprocal of that object. And so you end up with 2 to the negative 3 is obviously just 1 over 2 cubed, or 1 over 8. What about fractional exponents? Nope. Fractions, right? You're thinking of this. Yes. But what happens when my exponent itself is a fraction? It's roots. So here's the rest of it. Okay? You've got you have powers, exponents. They're still on top. They're what you think they are. But the root, like a lot of people refer to this symbol as that's a square root symbol. No, actually it's not. It's a radical. A square root symbol, no, it's what you think of as a square root. But that's not a square root, and it's the same symbol. It's a cube root, or a 4th root, or a 9th root, or a 100th root. It doesn't matter what root you're taking, this radical, okay, whatever index you see written out front, that's automatically what root it is. If it's not written at all, like this one, it's automatically a 2. It's a square root. You don't have a 1 root. That's like taking something to the first power. You don't even write 1 up there. You just write it. So that's kind of the idea there. Okay, when you do these roots like this, you simplify if you can. And if you can take certain roots, if I had a cube root of 4, I would take it. I can take the cube root of 8, can I? What's the cube root of 8? It would be 2, because 2 times 2 times 2 is 8. So when I'm taking multiple roots, or whatever, if I can do them, I go ahead and simplify them. If I can't, I leave them like this. Any questions on the basics on our review part here? We're good? Can you go any further than that? Not without a calculator. And I didn't. If you had to go to a decimal point, I didn't want you to go any further than what you see right there at just the cube root of 4. All right, so let's move on to the next point. Let's talk about the functions itself and just basic pieces. An exponential function. Now, this could be growth or decay, right? You're going to have a couple of pieces. You've got A, and you've got B, and you've got X. So let's define a couple of those parts. So obviously the exponent, that's the exponent. I'm not really going to make a big deal about that. B is what we call the growth factor. If you go back to the example that we opened up with, where you save a penny on day 1 and you double it each time, what's the growth factor? How much is it growing by each day? It's growing by a factor of 2. So if we were to write out that example, what would the penny example be? It would be what to the x power? 2 to the x. I'm doubling factors, right? The a value is going to end up becoming what we call the initial value. The initial value basically says, this is what number I'm going to start with. Well, 2 to the x has a 1 out front, right? So if we just write that down for a minute, if we had y equals 2 to the x, then my b is 2, so my growth factor would be 2, and my initial value would be the number out front, right? So what's the number out front of all that? It's 1. So what is 2 to the 0? 1. What number? How much money did you start with? 1 penny. So that's my initial value. If I had been like 5 times 2 to the x, could I multiply 5 and 2 together to get 10 to the x and it'd still be the same thing? Absolutely not. Never, ever, ever does that ever work. Order of operations is if you can't take that 2 to the x, in other words, if we're looking at this, y equals 5 times 2 to the x, that power has to be taken first. Powers have to happen before multiplication happens. Listen, that is a common mistake that I see a lot of times. Make sure that you are taking concern, you take care of that powers first, and then when you're done with that, then you multiply it times whatever's out front. So be careful. That can't be multiplied like 5 times 2. That is not 2. If x is 1, then I'm going to get 10, because 2 times 5 is 10. But if x is 2, that's 5 times 4. Okay? That's 20. If I multiplied first, I got 20 or 10 squared, I'm going to get 100. That's not the same thing. So be careful. All right, let's look at the picture of the graph. You're going to see 3 points. You've got 1 over b, okay? You got negative 1, 1 over b. You've got 0, 1, and 1b. What is b? Why did I use the letter b? Because b is right there. It is called the base of my exponent. So when you go to graph this, I'm trying to streamline the process of graphing. You can do this in really complicated ways, or you can do this in real quick ways. But in order to do it the way that I'm trying to teach you, then you need to know a few things. Primarily, I need to know these 2 graphs. Okay? One represents growth, one represents decay. It's not that I have to memorize a whole lot of pieces about that. Notice the points on both graphs. Negative 1, 1 over b. All right, you got this point here. Then you have the point 0, 1 and the point 1b. Notice the points on this one. They're exactly the same points. So when I go to graph this, I don't care if it's growth or decay. If it's growth, it's still the same points as it would be for decay. So you might want to write this down. For growth, For growth. So for B, for this side over here, growth, my value for B is going to be greater than 1. Always. For decay, B is going to be between 1 and 0. You will not deal with 0 being as B, and you won't deal with B being 1, because 1 to any power is what? 1. So you're going to get 1 times 1 times 1 times 1 times 1 ad nauseum, and you're done with it, right? It's the same thing, it's just monotonous. And so for growth, you're always looking at, oh, my B is greater than 1. For decay, my B is always between 1 and 0. Now be careful. There are some exceptions to this rule. If I throw in some negative signs and I start reflecting this over above the x and y axis, I could get some reversals in growth and decay. Okay, we'll play those out when we get to them. Let's talk about the analysis part over here. You see all this, right? So when I talk about, we're going to analyze a function. Okay, when we analyze a function, these are the pieces we have to do. Okay, now, exponential functions are actually not that bad because about half that stuff stays the same for every single one of them. So I don't really have to think about it. Any questions so far? Over here, here's some mumbling. You good? Yeah, yellow's not the best choice. Okay, B. Let's look at these over here. You've got domain. What's the domain for both of these? They're both going left and right, no breaks, no stops, all real numbers, piece of cake. Every exponential function has a domain of all real numbers. Lock that down. Memorize it. Don't even think about it. Okay? Range. This one's different. Every exponential function could have a different range. I'm going to look at this graph here, right? What's the range for the function for the growth function? Y is greater than 0. What's the asymptote right there? It's right at 0, right? It's right above that green line, but I just put it there so it wouldn't be exactly on top of it. Okay? Every exponential function without a vertical shift, and I'll put this on the screen in a minute, without a vertical shift always has an asymptote at 0. Y equals 0. And it's really, really important that you write down y equals 0, because when we go to logarithms, it's x equals 0. So if you just write down 0, I'm not sure which one you're talking about. Do you mean the vertical line or the horizontal line? These are horizontal, so they're y equals 0. All right? So the range plays a part in that. It says always my numbers are always above 0, so y is greater than 0. What about symmetry? Does that have any symmetry? Is it odd or even? Nope, no symmetry. Okay. What about extreme points? Does it have any maximum or minimum values that you could point to? Infinity is not a point. So don't refer to this, oh, the maximum is infinity. That doesn't make sense because there is no limit to infinity. Basically you said the limit is that there is no limit. Just don't say a limit. There is no limit, right? So that's like talking in circles. So if there isn't a point, you can say, oh, it goes up to that one point, and right here is where it's at its peak. Or right here is at its minimum value. If you can't tell me that exact point, then there exists none. In this case, there is no minimum, and there is no maximum. Now look at that. Look. Isn't 0 a minimum? It never gets there. If you were to pick a number, you can't pick 0 because it's not on the curve. But if you were to pick a number, I could give you a number that's even closer to 0 every single time. Because it gets infinitely small and infinitely close to 0 and it will never get there. Ever. Just like it's going up. It's never going to reach a maximum value. It's going to continue to increase. You pick a larger value, I'll pick the next one that's even bigger than that. Okay. What about asymptotes? We talked about that. What about increasing and decreasing? Shh. This used to be a challenge for a lot of you, but for these graphs, it was easy. Look at this side. Increasing or decreasing? Increasing over what interval? Negative infinity to positive infinity. The whole thing is going up, up, up. That's why we call it exponential growth. What about the left side or the right side? What about this side? It's increasing from negative infinity to positive infinity. It doesn't ever change directions. It's always going down every time. So intervals of increasing, decreasing, this only has one direction. It goes either up or down. So your interval would be from negative infinity to positive infinity, and whichever way it works. What about end behavior? That's a little tricky. So if we had f of x goes to, as x goes to negative infinity, what would it be? As x goes to negative infinity for the left graph right over here, what's happening to the y values you get over here? It's going down to what number? It's going to 0. So as we go to the left side of my graph, your y value is coming down, 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 and it's getting close to some number. What number is that it's getting close to? 0. Okay? If you do on the other side, if we look at f of x, as it's going to, as x goes to the right side, which would be positive infinity, what is on the right side of that? Where's f of x? Where's my y value going to? Good. You're looking at y values. How high or how low does it ever get? Well, on the left side, it's actually got a bottom. It's got what we call a limit. Horizontal asymptote is called limit. It can't ever get below 0. So it has a bottom in behavior. It's going to get close to this number and never ever reach there. What about for this side? As f of x as x goes to negative infinity, what about that one? What's happening here? Good. It's going up, so it's going to go to positive infinity. And then f of x goes to, as x goes to positive infinity, or the right side, what's happening to my y values there? Yeah, it's kind of reversed, right? So now it's going back to 0. Now, so just to connect a few things, in behavior and asymptotes are always going to be connected. You can throw range in there. In behavior, range, and asymptotes are all going to have something to do with each other for exponential functions, because they all deal with that horizontal asymptote part. It affects all of those things. Questions? What about continuity? Continuous or not? How do I determine continuity or not? Good. If I can draw the entire thing without picking my pencil off the paper, continuous. If you have to pick it up at any point in time to skip over something or to go to draw the second part, not continuous. Or you use the word discontinuous. Questions? Okay, that's the analysis part. Let's talk about the actual graphing part physically. Write these coordinates down. All right, so you're looking at graphing y equals 2 to the x. Your base is 2, your exponent is just x. We're going to be looking at the parent function for this. Now, something that's different about exponential functions, the parent isn't necessarily unique, because this parent function is going to be the parent just 2 to the x. So anything that has 2 to the x or transformations of that, it's going to have 2 to the with an x and the exponent. 3 to the x will be different. 10 to the x will be different. 1/2 to the x will be different. Okay? But the process of graphing any of those is the same. So try to generalize this into what those would be. Right now what we're looking at are the generic coordinates that we'd start graphing from. All right? So if we apply this, if you see up there I've got the y values, you got 1 over b, 1 and b. That's not a 6, that's a b. And that's what this is. The b is the base of the exponent, right? Intentionally written as b, because if I used any other base, then it would be specific to that number. So if I put that down in terms of just the actual coordinates, then this is what I would end up with. -1, 0, 1. And when I graph exponential functions, this is what I start with. Even if I have lots of crazy transformations on my graph, I'm still going to worry and change things based on this. So let's go ahead and put those points on the graph. So there are 4 things I want you to focus on when you're graphing this kind of stuff. There's 3 points and an asymptote. If you can graph these 3 points and an asymptote, then graphing this stuff is not really a big deal. Okay? So take a minute. I'm going to let you finish that, and then we'll move on in a minute. All right, so when you're looking at, I'm going to write down the generic form of our exponential functions. It looks like this. It's y equals a times b to the x minus h plus k. These are a, h, and k that you know and love, that you've missed so much since last semester that you're super excited to see them come back. I know, right? The benefit of this, you already know what they do. You know that A talks about stretches and shrinks and reflects over the x-axis. You know that H shifts it left and right, horizontally. You know that K is a vertical change, up or down. If you read my little statement above that, K, right, K is that vertical shift. So if I can tell you what K is, I know what my asymptote is without any thought. Oh, K is -2. Put a dotted line right there at the horizontal line, x equals or y equals -2. I find my 3 points, boom, boom, boom. I'm either going to be drawing it up or drawing it down for exponential growth or decay. But I know where my limitations are, my limits. Make sure that you go through that. Questions about any of that before we go on? Let you try one for yourself. All right. All right, you try this one. I got 3 for you to try. Try that one right there. I'm going to give you a few minutes, see what you can do. Okay. Let's talk about some of these graphs. If I look at the first one, let's just verbalize what the change is. The difference here is we now have, instead of 2 to the x, we now have 2 to the x minus 1. So that -1, if you go back and think about what I drew on the board a minute ago, that h inside, what is that going to do to my graph? It's a horizontal shift to the right 1. You learned this back in 9th grade. We also did it last semester. This is not a brand new concept. A lot of you caught that real quick, so it's really good. I'm going to go ahead and I'm going to write in the original points, right? So this is the before coordinates. I'm going to write in the before coordinates so I kind of give myself a starting place, and I'm going to change the coordinates that need to change. So the benefit of the method I'm showing you now is it will work for any type of problem. It doesn't matter how complicated the changes are. The only thing that you're going to do is you're going to change the coordinates, and then you're just going to graph these new coordinates and draw the line just like you've already done. Okay? So let's draw the old ones in as -1, 0, 1. No big difference, right? And it was 1/2, 1, and 2. It's always, remember, it's 1 over b, 1, and b. That's going to be permanent. Now, I've transformed it a little bit, so I've got to change a few things. So let's do the after coordinates here. So we have our new x and our new y. Okay, so listen carefully. If I shift to the right 1, do I change any of the y coordinates? What am I changing? What do I do to x? I'm going to add 1 to all the x's. So 0, 1, 2. So here, I just added 1 to all the x coordinates. Does that make sense?
So why did you add 1 again?
I added 1 because I'm shifting to the right one. So if I on the x-axis, if you go to the right one, what would you do to the x? You added 1. If I went left 1, I'd be subtracting 1. So does the y-coordinates change? Not a bit. So let's put those back in like we had them. 1/2, 1, 0. Let's put them there. Now let's go ahead and graph those points. So we have the point 0. Let's put these points in there. So 0, 1/2 is the first point. It goes right here. Then we have the point 1, 1. And the point I should probably fix that. Hold on. I got what's wrong with my y coordinates? Yeah, it's going to be 2 over there. Sorry about that. So that'll be 1 and then 2. So go up here, go over to 2 and to 2. And so you got this. What's my asymptote for this graph? It's still 0. So let's go back and put that asymptote in there. And so that would be my graph. It just took all my coordinates from last time and I just moved them to the right one. Visually, if I would drew the other one first, maybe kind of dotted that in real lightly with my pencil, and then just shifted the points, all those points, over to the right one place. That would be the same thing. Let's try the new coordinates for this one, for B. So our original coordinates for x and y, 0. That's going to be -1, 0, and 1. This is 1 over 2. This is 1 and 2. But where does my foundation come from? It comes from looking at the base of the actual exponential function. If that had been 3 to the x, then these would be 1/3, 1, and 3. Whatever that base happens to be, that's going to change your original points. What is this x, this negative x, what is that going to do to all my values? It's going to make all my what negative? X. Isn't x negative right there? So all my x's are going to be negative. So my new coordinates, so you have x and y here. That'll be 1, 0, -1, but 1/2, 1, and 2 don't change. Okay? So I changed, this is a reflection.
Hey.
Hey.
Do you have an extra CD that was or something?
A blank CD?
Yeah.
I don't.
No.
I have no blank ones.
Okay.
Sorry. Okay, so this is a horizontal reflection. It's going to do this. It's going to go from this side to the other side. It's going to flip-flop over the x-axis, right? So it's going to change the sign for x. Okay? And so if I just switch all the x signs, and I've got the picture. So let's draw that. And so in this case, if we look at our coordinates, listen, we have -1, 2. So we have -1 here, 1, 2. And then we have the point 0, 1. That didn't change because that's actually on the y-axis. And then we have the point 1, 1/2. What happened here? It changed to exponential decay because of the negative x up there. But what's 2 to the x? Isn't that 1 over 2 to the x? So, makes sense. All right. What do you think is going to happen for the last bit here? So I'm not going to redraw the old ones again because we've done that enough times to know what they're going to be. What are my new coordinates going to be for this one? So A is is that a stretch vertically or a stretch horizontally? A stretches which way? Remember? It's a vertical stretch. So what's the vertical axis? What's the vertical axis? It's the y. So that 3 is going to magnify each y value by 3. So multiply the y's by 3. X's, it's just 2 to the x, right? So nothing's going to change about x. I'm going to keep all the x's the same. So -1, 0, and 1. But this time, I'm going to multiply the y values by 3. So 1/2 times 3 would be 3/2. 1 times 3 would be 3. And 2 times 3 is 6. So if we graph that, we'll have -1. So that's 1.5 there a little bit, right?
It's not 3 over 2.
3 times 1/2 is 3 over 2. Yeah. So 1/2 times 3 is 3/2. So 0, 3 would be here. And then 1, 6 would be here. What's my asymptote for this function? Do I have a vertical shift at all? No. I have a stretch. It doesn't go up any. So my asymptote is still y equals 0. So here's my curve. So now you've got 3 different examples of graphing and changing it. The only thing I did was change my original coordinates. The graph part's always the same. Asymptote, 3 points, curve. Take this and practice it.